All right, thank you very much for inviting me to KAS. Of course, I'd love to be there in person, but sometimes it's easier to do things remotely anyway. So I was asked to talk about this paper from 2 years ago, this 1811 one with Yasmin and Ian, they're the ones on the left. And I figured I'd also talk about some newer work that just came out, I guess, 2 or 3 months ago with Yulia Gerline and Rebecca Pestis, who are the ones on the right. So I'm going to talk about the first one first. But before I do that, just a quick overview on where we are with neutrinos. And I'd also like to say, if anyone has any questions, please don't hesitate to interrupt and just holler, and I will do my best to answer them. So here's sort of a historical overview of the neutrino oscillation picture. So there are 6 parameters in neutrino oscillations that we can measure in the standard picture. The first one measured is theta 2,3, which was measured by super K, and it hasn't gotten a lot better. It's gotten a little better, but not that much, and we still don't know if it's more than 45 degrees or less than 45 degrees. Super K also measured this atmospheric mass splitting, not very well, but over time it got better, and then with the addition of Diabay in around 2012 and Reno, that got a lot better. In 2000, Snow came on the scene and told us what theta 1,2 was, and then Camland improved that. But Snow didn't really measure delta m squared 2,1 very well, and so that one pretty much just rests on Camland. Theta 1,3, of course, was very tricky to measure, and then 2011 or so, T to K had a very slight hint of theta 1,3, and then Diabay and Reno suddenly measured it very well, and now it is extremely well measured, as we know. And delta is the last parameter to be measured, and in fact, it has to be the last parameter to be measured. And the reason is because if any of the other parameters are 0, then delta is non-physical. And so now we're just starting to get some hints. We know it's probably not in this region down here between 0 and pi, but that's about all we can say. So that's where we stand today. All right, so here's the overview of my talk. First, I'm going to talk about sterile neutrinos and why there may or may not be sterile neutrinos in the data. And then I'm going to talk about what it looks like to add in non-standard interactions and sterile neutrinos at the same time. Then I'm going to talk about some very new data from just a couple of months ago from the long baseline world, from NOVA and T to K, and how new physics with, in particular CP violation can resolve this very slight tension. All right. So why is there so much interest in sterile neutrinos? I think this slide kind of summarizes that. Theoretically, there's only a little bit of interest. At some level, there probably has to be sterile neutrinos to explain why neutrinos have mass in the first place. That said, that doesn't tell us what mass they ought to have. Maybe we can mute someone. Thanks. And then we also know that if there's a sterile neutrino with a mass of around a keV, that could be the dark matter with some caveats. And there's a possible hint for a 7 keV sterile from an X-ray line. This is in contention in the last year or two, but it still is a very interesting thing. Experimentally, and this is of course what I'm going to be focusing on, there are some hints for a sterile neutrino with a mass of around 1 electron volt. LS&D and Miniboon both see something that could be electron neutrino appearance with similar parameters, and the combined significance is around 6 sigma. These are where you see an electron neutrino appearing in what should be a pure muon neutrino beam. And this frequency of around 1 electron volt is not compatible with any of the other frequencies that I showed just a minute ago. On the reactor side from Diabay and Reno, there's a theoretical prediction for what this flux should be, and the number of events they see is less than that by around 10%. And this is significant at around 3 sigma. And this could be the case for electron neutrino disappearance with very fast oscillations. This relies on a theoretical prediction, which is, hopefully robust, but maybe not. And so, there's some issues there. There's also some evidence that this anomaly evolves with reactor fuel composition. So as the uranium and plutonium parts vary during fuel burnup, this anomaly seems to change with that, indicating that this is a nuclear physics effect, not a sterile neutrino effect. However, newer measurements from Prospect don't seem to be really consistent with that story. So more information is needed there. The gallium anomaly is related to some older solar neutrino experiments. And for these experiments, they used sources to calibrate them. And there was a deficit. So in some sense, this is very similar to the reactor antineutrino anomaly. And that appeared to be 3 sigma in this paper by Junti and Levetter from 10 years ago. But in a reanalysis by one of the same authors last year, they found the significance is actually much less. There's also some excitement 2 years ago at the Neutrino Conference when 2 very short baseline reactor neutrino experiments, and by short baseline, I mean about 10 meters or so, Neos and Dance saw some wiggles. And this is where they can actually see some, a couple of wiggles. And the significance they sort of claimed were, around 3 sigma. With more data and really with a more careful analysis, these are now both less than 2 sigma. So there's some interesting hints, but it's mostly LSD and mini-boom. However, coming in very hard are some constraints, and there's a bunch of them. Most of them aren't really strong enough to really rule out this LSD and mini-boom story, but 2 of them are pretty much ruling them out, and those are IceCube and Meetus plus. These are both muon neutrino disappearance measurements, and I'm going to talk about them in more detail. I should also say there was a note about the Meetus plus constraint from Bill Lewis right after, shortly after their paper came out, and that has been essentially addressed by the Meetus plus collaboration. All right, so here's some perspectives on this complicated looking story where there's a lot of measurements. Some of them are pointing towards maybe a sterile neutrino, and some of them seem to be pretty much ruling that out. So how do we connect all this into one picture? Well, if there is new mu to new E appearance, such as LSD and mini-boom might be suggesting, this requires both electron neutrino disappearance and muon neutrino disappearance, okay, with the same frequency. And the amplitudes, of course, there is some flexibility, but not that much because of unitarity. You can't go, if one of them were to be very small, the other one would be, larger than unitarity says is allowed. So you have to have both disappearance channels have to be observed. Now, all the experiments that show evidence for this are energy dependent only. Right? So LSD and mini-boom, they see something in a spectral measurement. Okay, the reactor antineutrino anomaly, well, it's just across all energies, but that's compared to theory. Meanwhile, the constraints from Meetus plus and IceCube, they leverage distance, and we can measure distance as well. There's not going to be a problem in knowing how far away Meetus plus's far detector is. And IceCube uses angle, to get a distance for their atmospheric neutrinos. And while there's, of course, some uncertainty in these angle measurements, it's unlikely that there's a systematic shift where all these angles in these bins are actually put into those bins over there. And so this is one reason why people, I think, take these constraint experiments more seriously than the experiments with evidence. Now, I should say that experiments like Neos and Dance, these short baseline 10-meter things where you would see a, 1 or more full oscillation wavelengths, that's pretty hard to fake. That said, the significance of those is now under 2 sigma. So they're saying basically nothing. But there's another interesting thing that's different between the experiments that might be seeing a sterile neutrino and those that don't. And those that might be seeing one have no matter effect. Okay, for diaband Reno, it's in vacuum. Also in mini-boom, there is some matter effect, but the energies are very low and the distances are very short. So there's, the effect is essentially negligible for anything you might stick in there. But Meetus plus is quite high energy. We're talking about maybe 8 GeV and fairly long distance, around 800 kilometers. And IceCube is talking about a TeV of energy, and the Earth, so 10,000 kilometers. So maybe what we want to do, and of course this is what I'm going to propose, is add in some kind of new matter effect type concept. And the idea would be that there is a sterile neutrino, as Ellison and mini-boom are suggesting, but IceCube and Meetus plus don't see it because this new matter effect somehow cancels it out and somehow takes us back to the standard 3-flavor picture. And so exactly how that works and if that can work is what I'm going to work through, and that's what this paper is about. So first, a brief review of what non-standard interactions are, and this is not exactly what I'm going to be talking about here, but just so we're all on the same page. When we talk about non-standard interactions, some kind of new neutrino matter effect type interaction, mean is something like this Lagrangian here, this is just an EFT Lagrangian where there's where I've integrated out some mediator, and the neutrinos and some light fermions are coupled with this, and the strength of this interaction is governed by these epsilon parameters with a whole bunch of indices here. Now, in general, producing models of this form that are consistent with charged lepton flavor violation constraints is difficult. However, there have been a number of models, in particular in the last few years, and actually this slide is now a little bit out of date. There's a few more from this year as well. So it is certainly possible to do this. Now, that is the sort of scattering side of NSI, but now NSIs also affect oscillations. And they go into the oscillation Hamiltonian like this. So on the left here, this term is the vacuum oscillation term. There's some masses and then some mixings. And then A is the matter potential, which is proportional to the neutrino energy, the density of the material, and it's governed by the weak interaction. And so this 1 is the standard matter potential. That's there always. And these epsilons are if you add in some new terms. So you can see you can get a whole very rich phenomenology from this. So just a brief reminder of what these Feynman diagrams look like. These top two are the standard model. The left one is the neutral current term where all flavors couple the same to all the fermions. And for regular 3-flavor oscillations, this has no impact because it affects all the flavors equally. But this electron one does have an impact via the charge current diagram with electrons in every material, because of course muons and taus are not in material. And NSI looks like, in some vague sense, this EFT diagram where some flavor comes in and maybe a different flavor comes out and something happens in between. In general, we think that this is probably there's some kind of Z prime, and for oscillations, the mass of the Z prime doesn't matter, but for scattering and other constraints, it does. Okay. So I'm going to do a very brief sketch of the model that we presented here because it's a little bit different than what's normally done. What we're doing in this scenario is including a sterile neutrino with a mass of 1 eV, which gives us the LSMD and mini-boon 6 sigma situation. And we're going to include NSI, so some Z prime with a mass of around 10 electron volts. And this only is going to couple to the sterile neutrino. And the couplings to the active states will come in, but they will be negligible. Okay. Now, this active sterile mixing, as you may be able to see, breaks gauge invariant, so that's a problem, that's bad. So to address that, what we do is we add in a Higgs doublet with this same U1 charge. It gets a VEV, but this VEV is going to contribute to the Z prime mass. And of course, we want the Z prime to be fairly light so we can get a fairly large NSI out of it. So that's not so good. How do we get a new Higgs that's heavy enough to evade collider constraints while still having a small VEV? To that, we add in another particle, a scalar singlet, and this is what gives the Higgs doublet its VEV, is through this. All right. And so then when you wrap all this up, you get that there is a new potential affecting sterile neutrinos that is dependent on the coupling to sterile neutrinos, the coupling to baryons, and the mass of the Z prime. And then what happens is now we get the matter potential, which is for oscillations, which is typically just these top 3 terms, the charge current term for electron neutrinos, the neutral current terms for the active neutrinos, and typically there's a 0 here. So when you're dealing with sterile neutrinos, these neutral current terms matter because sterile neutrinos don't have them. But now we're adding in an additional term that has some free parameters in it. And we parameterize this in terms of this epsilon SS. Now, there's also the fact that you get ZZ prime mixing, but the parameters evade that constraint, so that's not a problem. We're actually many orders of magnitude below that. There's also fifth force constraints and stellar cooling constraints and effective constraints from cosmology. We're consistent with all of those. So this is consistent with all the astrophysics. So moving on to the oscillations, how does this, how do we see this in experiments? So, ice cube is sensitive to sterile neutrinos, and as I said earlier, and they have a particularly strong sensitivity due to a parametric resonance. And this is kind of a unique and kind of bizarre phenomenon. What happens is muon neutrinos, in general, at these energies, they don't oscillate and they don't experience any significant matter effect. However, if there's a sterile neutrino, because they don't experience this neutral current process, there is an effective matter effect. And what happens is the core, the size of the core of the Earth is just right, such that there is one sort of oscillation in that region for neutrinos to the right energy. And it turns out the energy is around roughly 1 TeV for delta m squared 4.1 of around 1 EV squared, which is, of course, this is the region of interest. And so what you see here is, and this is a plot from IceCube. This is not their data. This is just what would happen for some benchmark parameters for anti-muon neutrinos. In general, there's no disappearance. So this whole thing is blue in the standard model. But for a sterile neutrino, there is a big dip right here. Okay. So this plot is in terms of zenith angle and neutrino energy. And zenith angle of -1 is coming straight up out of the Earth through the core. The zenith angle of 0 is, horizontal sort of Earth skimming. And basically what happens is they take this region on the right where there's not any, they don't expect any significant effect in either the standard model or 3+1 scenario. And this kind of is their sideband measurement where they constrain what the flux is and all their experimental details. And then they take that and they look over here and they say, well, do we see something different? And so even if they can't measure the energy very well, seeing such a dip feature is a pretty clear signature. Okay, and they don't see one, of course. So here's another way to see the same thing. So on the left, I've plotted the neutrino disappearance probability. Muon neutrino disappearance is a function of neutrino energy. This is 1 TeV here. And on the left is neutrinos, and on the right is antineutrinos, right? And the black is the standard model, just 3 flavors. And you can see it's almost exactly 1, for the entire energy range. This is roughly the energy range that IceCube can see. This is where their data is. And this is for cosine zenith angle of -0.8. So it's pretty much going right through the core. Now, for the sterile neutrinos at the best fit point from LSMD and mini-boon, we get the green dashed curve. What you can see is, okay, it's doing a little bit of wiggling. It's a little bit lower, but IceCube is not very precise, so they probably wouldn't notice this. However, for muon antineutrinos, there's a huge dip going down about 0.5. So even though the mixing parameters in question here are a little bit small, the effect is very large due to this resonance. And the location here is a function of the delta m squared. Now what we see is if we add in a non-standard interaction in the sterile sector of what we're going to see in a second is the best fit point, we get back to this purple curve, which is really close to the standard model, and it's probably indistinguishable in IceCube. And so that's sort of the idea. So here's the parameter space scans. This is in terms of the mixing angle on the x-axis and the delta m squared on the y-axis. The blue is the region preferred by LSMD and mini-boon. This is where you want to be, and consistent with other oscillation, most other oscillation constraints. And they want to be out here to explain that data. And here I fixed, so that there's 2 mixing angles in play, theta 2,4 and theta 1,4. And I fixed theta 1,4, which is more about electron neutrinos, to that from the reactor antineutrino anomaly. This is the thing from Diabay and Reno. I fixed it to that, the number that those experiments prefer, and then you get this region here. And IceCube mostly, disfavors that. That's the black region here. So everything to the right is disfavored by IceCube. However, if we add in this new interaction and marginalize over that, going up to an epsilon of 1.7, which means that it's about the same size as a weak interaction, which is pretty strong, that actually this constraint completely goes away. And that's for the reason we just saw. And so we can see that we can have a sterile neutrino with the parameters preferred by LSD and mini-boon, and IceCube wouldn't see anything. Also, I'd like to point out that there's another paper investigating some similar things, but without a model to fully explain it. So here is the significance of this in terms of, as a function of this epsilon parameter, where I'm marginalizing over those sterile parameters. sorry, where I'm fitting to the stereo best fit parameters. And what we see is, what I'm comparing here is the chi-squared between the 3+1 scenario with non-standard interactions to the 3-flavor scenario. And I'm looking at ice cube data alone. So if we include the 3+1 scenario but no new physics, we're at the epsilon equals 0 point, and we see that that's disfavored right around here, at around 15 units of delta chi-squared. So that's what we saw before. They pretty strongly disfavor the best fit point. But if we include this epsilon parameter, we see we can actually completely alleviate that tension. In fact, do slightly better. Okay, not a lot, but ice cube alone slightly prefers a scenario with a sterile neutrino and a new interaction at 1 sigma. I mean, and plus we're adding in several new parameters. So this in of itself is not something to get excited about, except that it also handles the LS&D and mini-boon 6 sigma situation. So that's very nice. There's also this interesting dip, which is interesting sort of from a theoretical perspective. Why is there such a sharp preferred region here that's just very narrow? And what this is, if you check the numbers, you'll see that this is at epsilon equals -1/12. And if you convert it into the Hamiltonian framework, you'll see that this is actually the exact same as the neutral current contribution. So at this point, where the sterile neutrino has the same neutral current, that is, it's treated like an active neutrino via this new interaction, not via the regular Z boson, then actually that's a great fit to the data too. I mean, that's slightly disfavored at 1 sigma, but that's pretty good. So we see is that the introduction of NSI compared to a sterile neutrino alone changes the delta chi-squared from 15 to -1. So it's 16 units of delta chi-squared improvement over a sterile neutrino scenario. So I think that's pretty great. All right, so that's one of the main constraints, and we've crossed that off the list. The next one up is Meetus plus. So Meetus plus also has an interesting capability to constrain sterile neutrinos, and they have this very nice graphic which sort of shows that. So on the left is the near detector, and the right is the far detector. The lighter gray regions are those where they expect more events, and what you see is that they're sort of, so the black curve is the standard model, the 3-flavor oscillations, and normally use the near detector to constrain the far detector, but for the sterile scenario, what you do is kind of the opposite. You kind of want to look for the signal in the near detector given a measurement in the far detector. And they use a full fit, including all the energy and spectral information from both detectors. And that's how they get a fairly powerful constraint. All right. So we plug that into our scenario. We plug that into this with the non-standard interactions, and we see what we get. So we have this blue curve, which we saw a second ago, which showed that, for example, an epsilon of -1.5 looks pretty good for ice cube data with the LS&D mini-boon sterile point. And we plug in the same LS&D mini-boon sterile point to Meetus plus, and we get this orange curve. So without non-standard interactions, they disfavor the LS&D mini-boon point at pretty high significance, around 25. Unfortunately, they don't really help very much. This new interaction doesn't really help with Meetus plus a lot. In red is the combination, where we just summed them up before marginalizing. So, the ice cube situation is still a big improvement, but the Meetus plus not so much. So what we see is both of these experiments with just a 3+1 scenario these experiments disfavor that scenario at delta chi-squared of 40, which is pretty bad. And the introduction of this improves that down to 26, which is this dip right here. And that improvement comes almost entirely from the ice cube side. So this is not so promising. So what's going on? So Meetus plus doesn't work very well. So we decided to look into this a little bit more. So this is what the far detector would look like, kind of the same plot we saw a second ago. And the black is the blue is the standard model now. And the introduction of a sterile neutrino is shown in green. And that's an overall reduction in the rate of 3.3%. So that's roughly why they disfavor this. There's also some spectral information. All right. Now, if we add in the NSI that we wanted before, it gets actually worse. We go to the red curve here. And now we're at a 6.2% reduction. So that's why the NSI scenario wasn't really helping. And we can see here that when you marginalize over it, you get the chi-squared improves from 25 to 23. So basically no real improvement there. But throughout all of this, I had only been considering a scenario with theta 1,4 and theta 2,4. So only 2 of the 3 possible new mixing angles, mainly because it's a lot of parameters to scan. But why not include theta 3,4, which is reasonably expected to affect long baseline? Long baseline, so theta 3,4 has to do with tau neutrinos and how that mixes with the sterile neutrino. And in long baseline, neutrinos are tau neutrinos for a big portion of the way. So we include that and marginalize over that, and we get a best fit point of this teal curve, which is, okay, the shape is a little bit different, but we can see that the total event rate is the same now. So we can get at least the total event rate right. And in fact, the total chi-squared when doing the full fit to the Meetus plus data set is now down to 10.9. This is a significant improvement from 25. Right, so we're 25 with just a sterile neutrino. 23 is what you get when you include non-standard interactions. And when you include non-standard interactions and sterile neutrino and this theta 3,4 parameter, you mostly alleviate the tension. But we just messed around with theta 3,4 from Meetus plus. Now we have to check for ice cube, and it doesn't work. So what I'm showing here, the values of epsilon and theta 3,4 for ice cube on the left and Meetus plus on the right. And you can see here that Meetus plus actually finds a good fit or a better fit than before, and in particular has a non-zero value of theta 3,4 around 25 degrees or so. So that's why we get this big improvement by including that from Meetus plus. Now if we do the same thing for ice cube, the best fit region is right at theta 3,4 equals 0 or close to 90 degrees up here. But they do not want to be in this region right here. So, and we checked, and there's no way to patch these together. There's also some additional parameters in the sterile sector that you could turn on. These, there's 2 additional complex phases, delta 1,4 and delta 2,4, which we've taken to be 0. Some checks suggested that those don't work either, which is of course sad. This is the conclusion here. It sounds sad, but I think it's very interesting nonetheless. So here's sort of the summary for this portion of the talk. There's a lot of evidence for a light sterile in the data. We like to think that it shouldn't be there, and it feels like it shouldn't be there, but the evidence is there. Something is going on. Now NSI is a natural choice to keep the sterile neutrino there and get rid of the constraints from the other experiments. It can actually do that for ice cube, and it can actually do a pretty good job for Meetus plus. It just can't do them at the same time. And so I think that's a very interesting statement, that this kind of intuitive, the fact that the constraints leverage the matter effect in their own ways, and that is not the reason why there are some constraints and some hints for sterile neutrino, is I think a very interesting statement. So this is the halfway point. I guess I'm pretty much on time.
Hello.
Yeah.
Can I ask a question before you continue?
Yes.
So for this non-standard interaction of the sterile neutrino, do you use effective Hamiltonian approach with the dimension 6 operators? Or are you using this benchmark model with the sterile neutrino mass around 1 electron volt and G prime mass around? Okay, so this is the
10. Yeah. So you're asking. I presented this model where there's this new interaction coupling to baryons and sterile neutrinos for some fiducial parameters. But of course, there's some flexibility in these parameters, and all these parameters, we check their, all the details of the model are necessary for the astrophysical constraints and some other particle physics constraints like ZZ prime mixing. But you take all of that and you bundle it up, and as far as oscillations are concerned, there's only one number that matters, which is this epsilon here, which is a function of these couplings and the mediator mass. And we check that you can get an epsilon as big as you want, and then as for changing it around between -2 or +2 or whatever, is just small changes in these parameters, which is consistent.
So you don't have any constraint on the individual AE, A mu, or A tau in the
I
in
sort of
this.
glossed over this. So you need these A's, of course, to add up to -3 for for chiral anomaly cancellation. And so, but it doesn't actually matter for the scenario what you take them to be, because it turns out that the contribution to oscillations is negligible. So if you want to put more on the mu sector or more in the tau sector, for whatever reason, you're free to do that. We basically assume that they're all -1, but it doesn't matter.
Okay, thank you.
Yeah, good. Any other questions on this part? And we can also ask questions on this part at the end too, whatever. All right. Well, if someone hollers, then we'll go back. Shifting to some more recent work that is also related to some similar topics I was just talking about, as you may know, there was a big neutrino conference a few months ago, Neutrino 2020, where Nova and TDK released new data. These are the two state-of-the-art long baseline experiments. And this plot here shows what we've got. So on the x-axis is the constraint on the CP violating phase in the standard 3-flavor picture. And this is theta 2,3, which is the mixing yield that I showed you at the beginning. And you can see that Nova in the blue doesn't really know what it wants in life. But TDK is very specific, and it says that delta should be around here. It should be around 3 pi over 2. And in fact, that's the only region that Nova seems to think is not what delta is. And this is, I should say, this black curve here is from a slightly older TDK paper, but theirs is still basically the same. So this looks interesting, right? I mean, it seems like they're in some disagreement. So what does that mean? So I should say before I go on that the significances of everything I'm going to talk about for the rest of this talk are low, around the 2 signal level. So this is not about claiming that this is an actual discovery of some new physics with certain parameters, but it's rather answering the question, if our long baseline experiments disagree, what does that mean? Obviously, it could be an experimental problem, but as a theorist, I'm obligated to say what kind of new physics it could be, and is that new physics consistent with everything else? And in particular, of course, if these experiments continue to measure the same parameters, the same numbers, then the significance grows, and now we have to start taking this sort of thing more seriously. So the first thing I want to stress is the importance of how the mass ordering fits in with this. And I didn't include this in my introduction slide about the 6 oscillation parameters. But I think that measuring the mass ordering is important in of itself. We have to know what all the parameters in the neutrino sector are, and this is one of them. We have to know if the heaviest state is mostly electron neutrino or if it's almost no electron neutrino, and we don't know that yet. But it also has important phenomenological implications. It affects the sum of neutrino masses from cosmology. It affects things like Catrin. It affects neutrino stable beta decay a lot, and it could affect cosmic neutrino background measurements if we ever measure them. So it was quickly pointed out after Nova and TDK announced their results that this slight tension that we just saw, where they seem to be preferring different values of delta, is actually slightly resolved by swapping the mass ordering, which sounds a little strange. So I'm going to walk us through the mass ordering situation as it stands as of a couple months ago. So individually, Nova and TDK both prefer the normal ordering. Okay? They disfavor the inverter. This is about a 1.5 sigma effect for each experiment. The combination of them, however, prefers the inverted ordering, which sounds kind of bizarre, but that's how it works. That's due to these degeneracies between oscillation parameters. Now, super K atmospheric has some sensitivity to the mass ordering, and they prefer the normal ordering over the inverted ordering. All right, so we got a whole bunch of stuff going on here, but it turns out that number 3 on my list, the atmospheric part, is a bigger thing than number 2. Basically, while Nova and TDK prefer the inverted ordering, it's not by a lot. So the combination of them prefers the normal ordering. And then medium baseline reactors like Dibay and Reno provide some information, because while they're not actually sensitive to the mass ordering, they are sensitive to delta m squared 3.1 and delta m squared 3.2. And if you had a precise enough measurement of delta m squared 3.1 or 3.2, then you would have basically measured the mass ordering. So despite the fact that it kind of looked like the mass ordering was going to be normal, we now see that the evidence is a little bit, it's a little bit weaker, and the story is a little bit more complicated. So how do you keep all this straight? Well, this is a very hand-wavy way to think about why it makes sense that the combination of these experiments would flip the preferences, even though they both prefer the normal ordering individually. All right, so for long baseline experiment, appearance experiment, if you have delta of 3 pi over 2, the normal mass ordering, and you're in neutrino mode, the probability is comparatively large. And so by large, I mean something like 10 or 12%. If you flip one of those, it becomes small. By small, I mean around 6%. So by flip, I mean change delta from 3 pi over 2 to pi over 2. Or that is to say, flipping the sign of sine delta. Right? Flipping the sign of delta. There's no way to say that. That doesn't sound silly. I'm just going to move on. Flipping the normal ordering to the inverted ordering, or switching from neutrino mode to anti-neutrino mode. So this is how you can keep track of this. And you can see that flipping delta, the changing delta and changing the mass ordering is somewhat degenerate. And in fact, that's what happens in the T decay nova scenario. Now, it turns out that this doesn't fully resolve the tension. It's not actually a great fit to the data in the inverted ordering. It's just slightly better. So one might ask then, what kind of new physics might do this? And can the new physics do a better job than switching to mass ordering? So there's a whole bunch of things that probably all of which could play a role in this. But I'm going to focus on non-standard interactions because, well, that's the one we did, and we wrote this paper very quickly, so we did not do all of these things. But it'd be interesting to look at the other ones and see if they could work too. But the reason why this is a good idea is because T decay has at lower energies and shorter baseline, so it's kind of like it's in vacuum. Of course, it's not, but it's closer to that. While nova is at higher energies and longer baselines, so it has a fairly significant matter effect. So you might think that there's some new physics coming in that is like a matter effect, and that's going to make the experiments look different. Now, we want the CP violating phase to be different, so we think maybe it's a good idea to include CP violation in the new physics scenario too. So the rough picture that you should keep in mind is that T decay sort of is measuring the vacuum parameters, and nova is measuring vacuum plus the new physics, summed up in some sense. So I mentioned NSI before. In the context of 3-flavor oscillations, there are a lot of parameters. It can couple the different flavors in different ways. It can couple to, it can have a different structure with the fermions or with the Lorentz structure. Way too many to handle. We cut it down to 6 parameters, and really what we do here is we just take these off-diagonal parameters with the CP violating phases. And we take just one of these 3 at a time. So we do either E mu with a phase, E tau, or B tau. So you can relate these, this NSI scenario to a standard model scenario. And that's what this colorful equation here is trying to show. So on the left, you can think of this as maybe what's really going on, assuming there really is non-standard interaction. So this is what the Hamiltonian would look like. There's the vacuum term, u, m squared, u. There's the standard model matter term, which I'm calling A, and there's some new physics matter term. And what I can do is I can just write down this is the same as some different vacuum terms, some apparent vacuum terms, and the same standard model matter. And so what I'm doing here is what you would do is you subtract off this the standard model matter term, and you take, for some point in parameter space that you want to scan, you plug in, what the vacuum parameters are here, what the non-standard interaction parameters are here, and then you diagonalize it. You find the eigenvalues and eigenvectors, and this is what an experiment would measure. Okay, so this is what T decay would measure if they did their analysis without without realizing that there's non-standard interactions. And of course, they did not include non-standard interactions in their fit. And so this is exact, so this is handy. Now, we can do some analytic estimations of how big this effect is going to be. And what we do is we assume that that NSI is the explanation, which of course, it may or may not be, it probably isn't, but we make that assumption anyway. And we assume that non-standard interactions only affects delta. Okay, here we can see it's really affecting all the parameters. It's affecting all the delta m squareds and all the mixing angles and delta. But we assume that delta is the main thing that's affected here. So similar to what the equation on the last slide is, what you have is the probability. So this is sort of in terms of the true reality. There's some non-standard interactions and some true value delta. And this should be the same, up to some corrections, as the probability for no new physics and some inferred incorrect value of delta. And this should be this should work for both neutrinos and antineutrinos, and for both T decay and nova. All right? And the idea is that because they measured something different, they actually both point back to the same true value of delta and the same true value for new physics, but because they're at different baselines and different energies, the effect of these epsilons are different. And that's what we're going to see. So you can work out some algebra, and you can estimate the magnitude of this effect to be around 0.2. And you can do some consistency checks, and these numbers all make sense. Basically, you know, if these experiments measure the same thing, so if delta T decay, that is what T decay thought they measured, assuming doing a regular 3-flavor fit, and what nova thought they measured were the same, and of course this is 0, and then you have no new physics explaining this. If the matter potentials were the same, then you would need an infinitely large new physics effect, because this new physics effect is leveraging the fact that the matter potentials are different. So if they're the same, then it doesn't work. And then you can also check that the theta 2-3 dependence is right, and that's why epsilon E mu is a smaller new physics effect than epsilon E tau. Now that tells us what the magnitude of it is, but it doesn't tell us what the phase of this new interaction is. So again, under this ansatz, what you find is that sine of the true value delta and plus this phase is equal to 0, which is a pretty powerful statement. Now it doesn't tell you whether or not cosine delta is, cosine of this quantity is +1 or -1, but you can actually pretty easily check based on the matter potential and the fact that T decay seems to be measuring sine of delta equals -1. And from there you get this. And what this means is that, you know, very roughly, again, as I said before, T decay is basically measuring the true parameters, or more so. So you assume that the true value delta is what T decay measured, and that the phase, then that tells you the phase has to be 3 pi over 2, okay, of this new interaction. So that's our prediction. You can also do the same thing and figure out what the true value delta is. There's actually some slight shift here. And it turns out that because T decay is measuring something close to -1, this actually is indicating that the true value of sine delta is, you know, may well be less than -1, which of course is not physical. This is, you know, in effect, this is showing the weaknesses of this approximation. But in principle, what happens is there's some true value of sine delta, then T decay measures something slightly larger, and nova measures something slightly larger than that. And so that's what one would expect if NSI with the explanation here. So one would expect that T decay would start preferring something a little bit larger than -1. All right, so I did a bunch of hand wavy approximations, you know, taking theta 1,3 to be small, and delta m squared 2,1 is small, and all that stuff. But are they actually the right numbers for what goes into describing these data sets, and how significant is all of this? So at some point you have to actually crunch some numbers and not just eyeball the plots, right? So we approximate the experiments as counting experiments for appearance mode, and we present all the methods of our analysis, which is something that most other papers like this don't do. So for appearance, what we say is that it's the appearance probability plus, you know, weighted by some factor x, plus the long sign lepton. So this is, you know, so in neutrino mode, you have the probability of neutrinos to go from nu mu to nu e, but you also have the probability for antineutrinos to go. And this is, you know, necessary to include because when you're in neutrino mode, there are still some antineutrinos being produced. We then fit this to nova and T decay present their the expected event rates for certain fiducial parameters. And we can fit that and extract what these coefficients are. So x is basically the flux times the cross section times the detector volume times the efficiency and some other experimental details. Y is the same thing times the wrong sign lepton contribution, and Z is the background rate. And we do this for neutrino mode and antineutrino mode, nova, and T decay. And we find that actually this wrong sign lepton thing matters quite a bit, in particular when you're in antineutrino mode, because in antineutrino mode, neutrinos are produced at a moderate rate in the beam, and the cross-section is larger. So if this is important. For disappearance, it's a little bit trickier. We, for NOVA, this paper from Fermilab and Brazil, so the Brazilian team presented some simple expressions. And then for T decay, we used their likelihoods for delta m squared 3.2 and theta 2.3. We made some assumptions that are probably okay. Now, this alone is not enough. You cannot extract the oscillation parameters you want really from any one experiment. You need inputs from other experiments. You always do. Okay, so you need to constrain theta 1.3 from something else. So we use the Diabet measurement because Diabet is in vacuum and it's quite precise. So non-standard interactions won't affect this. And then for theta 1.2, we use Camland, which tells us theta 1.2 and delta m squared 2.1. There's a little catch here, which is that Camland only tells us the absolute value of delta m squared 2.1. They don't tell you if it's positive or negative. Snow tells us that it's positive, and that's because of the matter effect. But the problem here is that I'm messing around with the matter effect, so this could be a problem. However, it turns out that because Camland tells us the absolute value of this, Snow only needs to tell us the sign. But if you include, new physics and if you include a new matter effect and it doesn't exactly cancel this, it doesn't exactly change the sign to the other one, it won't work. And it turns out that we're not in that region of parameter space, so that's fine. So we constrain the standard oscillation pictures in terms of the Jarlskog, which is this quantity that tells you how much CP violation there is. And this is another way to see this normal ordering, inverted ordering scenario. So on the left, we do the normal ordering, and this is the Jarlskog on the x-axis, CP conservations in the middle, and then theta 2.3 in the y-axis. And T decay is the region in red. It's a little bit more precise because of the way their numbers shook out. Nova is this big blob in blue, and we see that when we combine them, we get the orange one, and this is bigger than the T decay one, which kind of suggests that they're not really in agreement. And this is of course because they prefer different values for the Jarlskog. But in the inverted ordering, again, T decay in red, Nova, which actually now sort of constrains something in blue, and the combination is a better fit. Things actually kind of go together well in the inverted ordering, and so the inverted ordering is very slightly preferred at delta chi squared of 2.3. So like 1.5 sigma or so. So here's the preferred regions for the NSI parameters. I show a few of them here. The other ones are in the backups if you want to see that. So the orange region is that preferred over the standard model. And on the left, I'm showing epsilon E mu, so the new interaction in the electron muon sector, and on the right is E tau. The x-axis is the magnitude of the new interaction, and the y-axis is the phase. So the standard model is on the left axis here. The dark gray is disfavored, and the blue star here is the preferred point. And we can see that in fact, CP conserving new physics, that is at 2 pi or pi, doesn't really do a very good job, right? You really want to be in the CP violating scenario of non-standard interactions. We also see that E mu does a little bit better than E tau, but they both are similar. And I've also drawn a constraint from IceCube. So IceCube disfavors everything to the right of this black dashed line. And it's somewhat in tension with this preferred region, but of course you could just sit in this little corner right there. So here's all the numbers. On the top I show the predictions that I mentioned earlier. We expect the magnitude to be 0.22, 0.24, the phase to be 3 pi over 2, and here are the best fit numbers. So for epsilon E mu, we get that the magnitude of the new interaction is 0.19, and the phase is 3 pi over 2. And this is preferred over no new physics at a delta chi squared of 4.4. Now recall that switching to the inverted ordering gives you 2.3. Instead, if you included new physics, you would get 4.4 improvement. And in fact, this is basically as good as you can do. So that is to say, we're describing the data correctly, as well as you can with this scenario here. The other scenarios do less well. Now that we have the numbers and we see that we want, what kind of values we want, we have to check, is this compatible with other constraints? So since the effective NSI grows with energy and distance and density, we want things with a lot of those things. So atmospheric neutrinos is a great place to look, and they provide excellent constraints on epsilon and u tau. In fact, they're way stronger than what you would get to explain this, which is why I didn't show it earlier. And then for epsilon e mu and epsilon e tau, the best place to look is long baseline appearance, right? NOVA and T decay. But of course, they're seeing some hints of this. So you would need something else, and atmospheric does an okay job there as well. So IceCube, as I showed, they slightly disfavor the best fit point, but not really. It's also, you know, looking very carefully at their plots, which I'm showing on the top right here, they actually, you know, very slightly disfavor zero. So I said all the significance were low. This is even less significant than that. But I can't help but get excited when I see something that appears to line up. And this is their constraint and preferred regions in epsilon e mu and the phase. It's the same parameters that I just showed. And they rule out everything to the right at, you know, whatever significance. And their best fit value is non-zero at a little over 1 sigma, and the phase is comparable to what the phase that we saw. You know, it's in the same region. Of course, this is almost certainly not anything, but nonetheless, I'm allowed to get excited from time to time. Super K can also do this. They're lower energies, so that's not as good for this, but they have lots of data, and it's, you know, better. It's a more precise detector than IceCube. They have never published anything with complex NSI. So you cannot do a direct comparison, but based on their constraint on real NSI, it's basically similar to that of IceCube. And I wouldn't expect it to be super different. But it'd be very interesting, and I've talked to them about whether or not they will do complex NSI in future analyses. Now, another great probe of NSIs is from Coherent, which I'm not going to talk about, although I'm happy to, if people are interested, which measured this SEVENS process, this coherent elastic neutrino nucleon scattering process, with pretty good precision, or at least decent precision. But it turns out that this, you know, it's a model-dependent translation into this oscillation scenario. So, you know, it only applies if the mediator mass is heavier than some limit around 10 MeV. You can also get around the coherent thing by shuffling around up quark, down quark, and electron couplings. These things don't matter for oscillations, but it does for scattering. In any case, even if you don't do any of that funny business, the constraints are still about the same as IceCube, or a little bit worse. So this is not a problem either. All right, I'm pretty much out of time. So to summarize, what I've shown is that IceCube and Meetus Plus, they just by themselves, looking at a 3+1 scenario, it's not compatible for LS&B, mini-boon, reactor antineutrino anomaly. But NSI can, you know, NSI plus a 3+1 scenario can, you know, completely ameliorate IceCube's constraint, and it can do a pretty good job for Meetus Plus as well. Unfortunately, we have to deal with everything at once, and that does not work, as we've seen. Now, I've also shown there's this interesting tension with NOVA and T decay. It might have to do with the mass ordering. It might have to do with new physics. If it is new physics, it suggests that there is an additional source of CP violation, and that it is not only compatible with atmospheric constraints, but testable in those experiments, you know, very soon. That's all I've got. Thank you very much.
Thank you very much. Oh, nice talk. So, any question or question?
Hello, I have a question.
Mm-hmm.
I'm curious about the possible UV to get the proper non-standard neutrino interaction, like including CP. And since you have took the Z prime model as an example, but as far as the CP is concerned, is it possible to get the proper size of CP just assuming this Z prime interaction?
Yeah, so that's a great question. So there's a couple of different directions that I can come at from that, that explain why I'm okay, why I'm not in trouble. I can see why it looks like I would be in trouble. First thing is the model that I presented for the sterile neutrino scenario is not necessarily the one you need to consider for the long baseline. So that's one thing. And you know, there's many models that are typically focusing on non-standard interactions with active flavors. Now, in these models, I've looked at them, and I don't think any of them mention CP violation in their models. However, I've talked to a number of these authors. They say that many of them can encode CP violation, but the fact is that actually there's very few papers looking at CP violation in non-standard interactions, so people don't really think about it. But you know, there's certain models involving additional Higgses, as does the one that I presented, and you know, these can have CP violation. And people, you know, they say, oh yes, of course this. You know, there was a model by Paul Dev and his team of people with some Higgs doublet scenario, and I asked him, and they get epsilons of around 0.2, which is, you know, pretty much what we need. I said, can this be CP violence? Oh yeah, definitely. It's not a problem. So I think these models do exist, but people haven't really spent as much time on it as they should.
I see. And also related to that, I just wonder if there's any dependence on the type of the effective operators, like vector-like or you know, the scalar, pseudo-scalar, vector, excel vector in their analysis.
So for the long baseline and for the Nova
both.
thing, we did not look at that. People have looked at that. So I will say for spin 1, only the vector part affects propagation. The axial part cancels out during propagation. So that's, I mean, you can do whatever you want there or nothing, it doesn't do anything. As for scalar, people have looked at this and you can get, it looks pretty much the same. The parameters in terms of whatever your UV complete model, of course, are going to be different, but the phenomenology in terms of oscillations, I think is pretty similar. But most people do vector, so that's what we did. That's basically, you know, I think it works with vector, and I think it may well also work with scalar, but it would be interesting to see that. Yeah.
I see. Yep. Thank you.
So,
anything else?
question or
hello, could you show the slide 36?
36?
Yes.
Yeah.
Yes. So when you combine NOVA and the T2K, the allowed region is the blue curve covers much wider region. For the normal ordering.
Yeah, for the normal ordering, so NOVA is in blue. TDK is in
sorry.
red. Yeah.
Okay.
Yeah. I mean, it's basically, the problem is while they both prefer the normal ordering, they prefer different values of delta. And so then there's this tension in delta. Basically NOVA, well, TDK wants to be down here pretty strongly on the lower side around -0.03. And NOVA doesn't really prefer that. And if they are down there, they want to be in the lower octane of theta 2-3, while TDK does not. So if you combine them, something has to give, and basically it doesn't work super well, which is why you end up, you know, kind of in the middle of nowhere. Yeah, sorry, I maybe should have done the legend differently.
Okay, sorry.
Yeah, good.
Any other question? Okay, if not, then let's thank speaker again.
So thank you very much.
Thank you.